Hello. I hope you're all staying well and mentally well during this quarantine or isolation period. I know it's been hard to be out of school, especially when you have schoolwork to do, and so I hope that you're able to do all right with that. A lot of you are working on the Momentum Lab this week, as you should be, and I've gotten a lot of questions about the evaluation section and the conclusion section. And since we haven't had any kind of post-lab, I thought we would do kind of a post-lab presentation. So the first thing we have to do with this is to be able to correctly calculate the change in momentum of each cart. So here's an example that we can look at. Let's suppose that we've got cart number 1 and its mass, let's just say for the sake of this, is 2 kilograms. Let's also say that its initial velocity, in this case, is 2 meters per second. And if to the right is the positive direction, that means it's moving at 2 meters per second to the right. And let's say its final velocity is 0.7 meters per second. So it continues to move to the right. And by the way, this will be an elastic collision. So if we look at cart number 2 for this example, let's say that its mass is 1 kilogram. Let's say that its initial velocity is 0 meters per second, so it's just sitting there, and the other cart will come up and collide with it, and its final velocity will be 2.7 meters per second. So it's also moving to the right, as you would expect. So if we look at this, sort of how it looks here, if this is cart 1, and this is cart 2, we know that cart 1 is moving that way and at 2 meters per second, and cart 2 is 0 meters per second, right? But after they collide, they're both going to be moving to the right. So, to calculate the change in momentum of cart number 1, we use the equation m for 1 times v sub 1 minus v naught sub 1. So this is read, the change in momentum of cart 1 is equal to the mass of cart 1 times the final velocity of cart 1 minus the initial velocity of cart 1. So if I substitute the numbers in here, I get 2 kilograms times 0.75. I'm sorry, it's just 0.7. So I can erase that. .7 meters per second minus its initial velocity, which was 2 meters per second. Right? So delta P1 would be the 2 kilograms, and 0.7 minus 2 is negative 1.3 meters per second. Notice how it's a negative number because the initial velocity was greater than the final velocity. And so this gives us delta P1 is going to equal negative 2.6 kilogram meters per second. And this is what I would graph for the 1 point for delta P1. Now if I go over to do delta P2, let's see if I can have any luck in changing the color of this pen. I'm still pretty new with this software, so you'll have to give me a little bit of slack here. So delta P2 then would be using this same equation, but I'm just going to put the numbers in. So we have 1 kilogram, that's the mass of cart 1, times the final velocity of cart 1, which is 2.7 meters per second. Oops. 2.7 meters per second minus the initial velocity, which was this, so that's 0 meters per second. So that's 1 kilogram times 2.7 meters per second, which gives us delta P2 of 2.7 kilogram meters per second. And these are the 2 points that you would then graph in your data set. So hopefully that illustrates that a little bit better. I know that there have been some questions about that, and people have been graphing, and some of the ones I've already received, they're graphing the mass versus the change in velocity and things like that. And what we really want to graph is, on a set of axes, delta P1 and delta P2. And by the way, it doesn't matter which you put where. But that's what we want to graph. And so you have to go through this process for all of the data points. So get rid of that, and we'll go back to the pen, see what we can write with that. All right, so once you've done that and you've plotted your points, you're going to get a line that looks a little bit like this. And then you're going to have the data points sort of like this. So notice that all the points are in quadrant 2 and quadrant 4. And they shouldn't really, you wouldn't expect them to give you a really nice graph, but they might. So let me show you one that that was done by students. And okay, so let's make this bigger. And then let's move it over here. I'll cover up what I had. So this is one that we that was graphed a few years ago by some students. And you'll notice that it's linear, and it has a really good correlation, right? If you look at this correlation right there, negative correlation just tells you that the graph is slope is negative. And then notice what the slope is. The slope is a number that's pretty close to -1. And so, get all this stuff in here. So when we look at this, we know it's a linear graph. So thankfully we don't have to linearize it at all. And if we know that it's a linear graph, then the proportionality is a direct proportionality. So we could say delta P1 is proportional to the opposite of delta P2. Now this negative sign doesn't do too much here, except the fact that it tells us that they're opposite. The same stuff applies with this proportionality as it would if it was positive. But it's very important that your data points are in quadrant 2 or quadrant 4. If they're not, then somewhere along the line you miscalculated or misrecorded. So any points you see floating around in quadrant 1 or 4 or 3, you should go back and take a look at those again. See if you calculated them right. So if we have this kind of proportionality, and then we know that the slope is given as about -1.05. And look at the units. Kilogram meters per second divided by kilogram meters per second. And those would cancel out at some point, which tells us it's like a dimensionless quantity, much like we would see with like mu or pi. Those also don't really have any units, but they do. You know, pi is the units of like centimeters over centimeters, and mu has the units of newtons per newton. This has the units of kilogram meters per second over kilogram meters per second. So then if we take a look at the intercept, it's a very, very small number here. It's -0.0212 kilogram meters per second. Now, if we were to go back and look at our data, we would see that this certainly falls within the 5% rule. So we can call it 0 by the 5% rule. Okay, so then if we were going to write an equation for this, we would write our equation to be delta P1 is equal to negative 1.05, and I think you should go ahead and keep the units in there because they do tell you something about what's going on here, times delta P2, and because of the 5% rule, we're not going to have an intercept on that. So that's a linear equation, which is kind of interesting if we take a look at this. So what is it telling us? Well, one thing it's telling us is that if delta P1 increases, then delta P2 decreases. So we can see that as the change of momentum of, let's say, this card increases moving this way, from whatever it might be to whatever the other one is. If, let's say, it starts with, let's see if I can change this color here. Let's say I have a momentum that starts right there and ends up right there. So delta P2, now if you look at this, it decreased because this is 0.2, and this looks like it's about 0.3. So going from 0.03, 0.2 is right there. So it decreased, but the momentum of cart 2 went from about, or the impulse of cart 2 went from about negative 0.2 to right up here, about negative 0.03. But it was an increase. So this increased as this decreased. And so that's what this statement right here is telling us, that the momentum of one increases, the other decreases, and vice versa. So that's important too. So it goes the other way. If delta P2 increases, delta P1 would decrease. So what does this mean? Well, it kind of tells us that if we look at this, that the impulses between the two objects are, my handwriting is bad enough, but with this thing it's even worse. First of all, they are in the opposite direction. So it's important to remember that impulses are vectors, just like momentums are, and they have the opposite directions. That's what this is telling us. As one increases, the other decreases, and vice versa. The other thing we want to look at is the slope. Now, if the slope is really close to -1, now yours probably will vary, it depends on accuracy, but it's about -1, which means that if I were to write this, what is the slope telling us? If delta P1 increases by 1.05, and I'll leave the units off, then delta P2 decreases by the same amount, because that slope is really close to -1. So the impulses are opposite in direction and equal in magnitude. Does that sound familiar to you? You ever heard that sort of people say equal and opposite, but of course they're not equal and opposite. They're equal or they're opposite. In this case, it's telling us that they are opposites. They are opposites to each other. So you know, for example, if the impulse on one part is, let's say, 5 kg per second, and the impulse on the other, because they collided, is -5 kg per second. So this is a big idea that the impulses are opposite of each other. Opposite in direction, equal in magnitude. And it has some rather interesting consequences. and that is that if I add these two impulses together, I will always get about zero, which means that the momentum of the total system of those two objects does not change. The system momentum did not change. And we're going to be able to use that idea a little bit later as we go through and solve problems, which I have a couple of videos out there for that, and I'll probably make some more if you need them. So, just to recap really quickly, you correctly calculated the change of momentum of each cart, and once you did that, you plotted them on a delta P1 versus delta P2 axis. When you did that, you got a linear graph with a negative slope, which told us that the impulses are proportional to each other. Or I should say the impulse of one is proportional to the negative impulse of the other. The slope turned out to be a number very close to 1. The intercept turned out to be a number so close to 0 we can call it 0 by the 5% rule, which gave us this equation. What that tells us then is that if the impulse of cart 1 increases, the impulse of cart 2 decreases, which basically means that as the momentum of one cart increases, the momentum of the other cart decreases as well, and vice versa. The two impulses are opposite in direction and equal in magnitude, which tells us in the end that the system momentum does not change. So I hope that that helped a little bit. I'm sorry if it was kind of fast. If you have any questions, don't forget you can come to the office hours from 10 to 11 on Tuesdays and Thursdays. I will be there to answer questions, or you can email me or text, and we will get things worked out. So good luck with that. And remember, do it on a piece of paper or in your lab report. Take a picture of each page and submit it through Blackboard. So stay healthy. We'll see you later.